Okay, grade 9, here we are, lesson number 3. This is about ionic bonds and ionic compounds. Now, we already saw this with our first chem unit, but only a little bit. Partially for review and partially because I know the two different classes had a little bit of different things going on in our first chem unit, we're going to just go through this and make sure everyone has the same foundation understanding of this key important concept for chemistry. So here's your template for today. Notice how we have a 2-pager. We have electronegativity bonding with one diagram, ionic bonds and compounds, other half the same page diagram. A little bit of space for rules, but naming. And you're going to do a table here of practice questions with drawing, naming, and analyzing ionic compounds as well. Okay, so first things first, let's talk about arrangement of valence electrons. So we reviewed this already, and hopefully you remember this as well from your notes and looking at all your various stuff you have from the first chem unit. The arrangement of valence electrons, how does that determine the reactivity of an atom? Can you remember? Okay, well, hopefully you remember the fact that the closer that an atom's valence orbital is to being full, either because it has almost full, like it has 6 or 7 valence electrons instead of 8, it's really close, or it's almost empty, it only has 1 or 2 valence electrons. Either way, it's not going to take a lot of electrons leaving or gaining to make it stable, and those ones are much, much more reactive. The elements whose valence orbital is already full are super stable and they will not react at all, very, very low reactivity, and those would of course be which group? The noble gases. They have a full octet, they are very stable and not going to react at all. And we often call this the octet rule because most of the time the valence orbitals should contain 8 valence electrons. The exception, of course, is helium and hydrogen, which both contain only 2 valence electrons if they're full, because they only have 1 electron in hydrogen and 2 in helium. But a good way to think of this, especially in terms of bonding and energy in bonds, is this potential energy. So which atoms are going to have more or less potential energy? You can kind of equate potential energy to reactivity, the potential to do a chemical reaction, to form a chemical bond, that kind of thing. Well, the ones with the most potential energy are going to be your alkali metals and your halogens, the ones that have 1 valence electron, or they have 7 valence electrons that are really close to having a full octet. Those are the ones that are going to have the most potential energy. The least potential energy, oh, see, look, there's a typo. The least potential energy is going to be in the noble gases, of course. So what I want you to do is take out your periodic table. If you don't already have it out, if you haven't printed one or you lost yours, please print one because you're going to need to be working on screen and you can't have it all on one screen. And you'll need to have it for your tests. So make sure you find a way to either print, or if you really can't figure that out, then copy it up by hand on some paper, a periodic table. If you are going to print it and you want a copy of the really big one that I gave my class, that you can tape together and fold, make a nice big color, easy to color in one, let me know. Just send me an email and I will share it with you, okay? So here I have 3 elements, K, chlorine, and Ar. So use your periodic table, figure out which family those 3 belong to, and then predict how much potential energy they are going to have. So pause the video and do that. Okay, so we start with K here. K is potassium. It has 1 valence electron here, and it is in the alkali metals, group number 1. And you'll notice because there's only 1 valence electron, it is going to be very reactive and have a lot of potential energy. All it has to do is get rid of that 1 little valence electron and it can be stable. So it's very reactive for that reason. And then we have chlorine over here. Chlorine, element number 17, is in the halogens. And you'll notice here its valence orbital has 2, 4, 6, 2, 4, 5, 6, 7. I can count, guys. 2, 4, 6, 7 valence electrons, okay? It has 7 valence electrons, which means it's 1 away from being stable, so having a full octet, so it is very reactive. It's a lot of potential energy as well. It only needs one more valence electron to be complete octet and be very stable and happy. And then here I have argon. Argon, element number 18, is a noble gas. And it has a full octet. 1, 2, 3, 4, 5, 6, 7, 8. It has very, very low potential energy. It's not going to react. It's really hard to even force noble gases to react. Okay? So it's very, very stable. So to become stable, to reach that full octet, atoms will do different things. There's three options. To form a bond, they're going to either share electrons, they're going to take electrons, or give away electrons to form sort of bond and then become stable. And of course, when I say electrons, I'm talking about valence electrons. It's only those valence electrons in the outer orbital that will do this. Other electrons in the inner orbitals don't go anywhere. They're stuck. Okay, so here we think about this. You have two atoms that both have high potential energy. When they form a bond, the molecule they form is going to have less potential energy as a combined set of two atoms. The two atoms that individually, some of the potential energy is gone. Why is that? Well, we talked about the way they get their potential energy is from being unstable. And if they form that bond, they have become stable. They now have a full octet, so no longer have the potential to react anymore. But so that energy doesn't disappear, of course. Energy can't disappear. Where the energy goes is now held in that bond. So a great way to get energy from chemicals is to break bonds and release the energy in them. Now, the way that the atoms will decide if they're going to give, take, or share electrons to make their bond and become stable is based on a property called electronegativity. So we talked about this as well in our previous, but I know it's been a while. So electronegativity is how strongly an element holds on to electrons. So if we have two elements that have very similar electronegativity, there's not a big difference between them, then they're going to share those electrons. Not one atom isn't strong enough to pull the electrons away from the other, so they will both just share the electrons. If one has a much higher electronegativity than the other one, then it will take, and then will lose if it has much lower electronegativity. So you look here, and we have an example with sodium and chlorine. They both one valence electron that happens to belong to sodium, but sodium has a much less electronegativity than chlorine does. So what happens is they're kind of fighting over it, if you will, with their little high heel boot things on. The chlorine will take the electron away, and then chlorine becomes negative, so it's an extra electron, and sodium becomes positive because it lost its electron. So now sodium has 11 protons, but only 10 electrons. And chlorine has 17 protons, but 18 electrons. So this is a negatively charged ion and a positively charged ion. So to draw this diagram into your notes, please. And this is an ionic bond right here. Oh, another typo. Jeez. Oh. Okay, so make sure you draw that diagram. Okay, we're going to look at the periodic table, and I want you to do is make note of the general pattern on your periodic table. Now, if you haven't printed one out yet, but you need to go back and add this when you do. So this periodic table has all the electronegativity values for all these different elements. You notice the numbers here, 3.04 for nitrogen, 3.44 for oxygen. It shows you the electronegativities. And they have colors to help show the similar ones are going to be the similar color, just to help you get an idea. Okay, so you look at this, what pattern do you notice? Where are the strongest, where are the weakest, that kind of stuff. Well, the single most electronegative element here is fluorine, 3.98, so it's always going to steal electrons. It's never going to share them or give them, unless it's forming a compound with itself. Then we have oxygen, the next biggest one, and the pale yellows, nitrogen, chlorine, and then we get to more yellowy, starting to go to green, bromine, hydrogen, sulfur, selenium. Noble gases, for the most part, do not have any electronegativity. These two here are a little bit different for reasons beyond the scope of grade 9 chemistry. So you're not going to learn why that is the case this year. I still chose this diagram so that it was very clear in other ways. Notice over here, the dark pink are very low, less than 1, most of them. How big are from like 1 to 1.5 or so. So which groups have the highest and lowest? Well, for the most part, group 1 over here, these are all really low, right? The lanthanide and actinides are all really low. The exception, of course, being hydrogen. Hydrogen is always towards it's a non-metal and really belongs kind of over here, but it's the first one. And then you notice here a lot of the non-metals have a lot higher electronegativity than the metals do. Some of these transition metals a little bit higher, but all is like pink and pale teal. Nothing in the greens over here. Okay, so make a note of that in your table. The electronegativity tends to increase going this way and increase going up as well. So it gets higher electronegativity as you go from left to right, and it gets higher as you go from bottom to top. Which makes sense because the strongest is here with fluorine. Okay, next part, let's talk about ionic bonds. So when we have electrons that are going to give and take valence electrons, when that happens between atoms, that forms an ionic bond. So ionic bonds are made where we have ions being formed from giving and taking of valence electrons. So since electrons are being given and taken, this means, just tells us about the electronegativity of those particular atoms, of those elements involved. So what does that tell us? Well, it tells us there has to be a big difference. There has to be a big enough difference between the two different elements involved that one is strong enough to steal electrons from the other. So the way a good way to think about this is the fact that most of the time, non-metals have really high electronegativity compared to metals. So in that case, when ionic bonds are always formed in a metal and a non-metal, and it's always the case where the metals become positive, or it's usually the case where metals become positive. They become positive charged ions by giving away electrons, one or more valence electrons, and then the nonmetals become negative by taking one or more valence electrons. So if we look at this little picture here, I have my sodium, which of course is a metal, and my chlorine, which is a non-metal. It has 1 valence electron. This one has 7 valence electrons. So to become stable, sodium is going to give a valence electron to chlorine. And then that means now sodium is positive, chlorine is negative. There's a little X electron here. And the negative positive attraction, that's the ionic bond. So if we go back for a second to our table here, look at sodium, 0.93, and look at chlorine, 3.16. Of course, chlorine is going to steal from sodium. Chlorine is way stronger than sodium when it comes to electronegativity. Okay, so please draw this diagram. I recommend you use colors to help show the electrons. And make sure you put the charges, positive and negative. That's really important. Okay, so when that bond is formed, something really interesting about ionic compounds and ionic bonds is those two atoms, those ions now, remain separate. They're not physically attached in any way, but they have opposite charges. This one's positive and this one's negative. So the opposite charges cause them to be attracted to each other. And that keeps them to the bonding. The bond, an ionic bond, is an attraction to these two ions, and that was formed by them giving and taking electrons. You can also draw this with a Lewis dot diagram where we have a sodium with only 1 valence electron, chlorine with 7, and that makes positive sodium with no valence electrons in that outer orbital anymore, and chlorine is negative with full octet of 8. So you can also draw it this way. In the homework, you can draw Lewis dot diagrams instead of Moore-Rutherford. But if you're not really comfortable with these yet, you can always do Moore-Rutherford first to then figure out the valence electrons. Remember, Lewis dot is the same rules as we're only showing valence electrons. We get to ignore all the electrons in the middle because they're not part of any chemical reactions. Just draw the symbol and then the valence electrons are on the outside. Okay, so ionic compounds have special properties. that's unique to them because of this type of bond they form, because they're ions and they have these two charged, or more than two, at least two anyway, charged atoms, ions making up the compound. They have very strict properties. So these are really strong bonds, and I often think of it as like they're attracted, they want to be together. They have this attraction, that's a strong bond. And that means they have a high boiling and high melting point. So there's a lot of energy to break that bond, to either change it from a liquid to a gas, the boiling point, or from a solid to a liquid, the melting point. Both of those things are pretty high temperatures, and it takes a lot of energy to do that. It's a strong bond. They tend to be solids at room temperature, and they have the really cool ability to dissolve completely in water because of their charges. When we talked about water being polar back in our earth science unit, and water has those dipoles, slightly positive, slightly negative charges. That's what allows water to separate ionic compounds. For a great example is sodium chloride, salt. Dissolves really easily in water. The negative dipoles come around the sodium, the positive dipoles go around the chlorine, and now we have salt water. And when ionic compounds are dissolved in water, they can then conduct electricity. Okay, so let's learn the rules for how to name ionic compounds. Now, luckily, naming ionic compounds is pretty simple. Naming molecular compounds is more complicated, and we'll get to that next lesson. So, since every ionic compound, there's only one possible combination between a pair of elements that can make an ionic compound, because there's only one way that every element can become stable. So, for example, here if I have magnesium and chlorine, because magnesium has two valence electrons, the only way that magnesium and chlorine can both be stable is if magnesium bonds with two chlorines. And then it gives one valence electron here, one valence electron here. So with sodium chloride, sodium and chlorine can only bond one way. I can't have an extra chlorine because there's no other valence electrons for that chlorine to get. It's only one valence electron, so only one chlorine can bond with it. Okay, so the number of chlorines differs based on how many electrons there are, valence electrons, in the metal it's bonding with. So the rule for naming is you write the entire name of the metal. So you'd write the whole metal name, and then you would write the name of the non-metal, but you change the ending to IDE. So for example, oxygen becomes oxide. Iodine becomes iodide, that kind of thing. So try naming these two compounds here. We have this one and we have this one. What are their names? Well, we have magnesium chloride. Magnesium is the same, that's our metal. And the non-metal, chlorine, we change the ending to IDE. And the second one, sodium chloride. I'm going to specify anything else, just those two, because only one possible combination between those two elements that can make it a stable ionic compound. Okay, so what we're going to do now is to practice. So we have 5 for you to practice, and what I've done here is given you an example, and then we have 5 other ones to do. So I've given you 2 elements here, metal and non-metal. I'm going to write down what's the positive ion and the negative, what's the charge going to be. So to do that, you have to know how many valence electrons. Because magnesium has 2 valence electrons, it's going to become 2 positive. Because chlorine has 7 valence electrons, it's going to become 1 negative. So I can figure that out based on their number of valence electrons. Then you're going to draw a Lewis dot diagram for the pair. The chemical formula, MgCl2, 1 magnesium, 2 chlorines, and the name, magnesium chloride. So here, lithium and phosphorus, calcium and sulfur, aluminum and oxygen, potassium and phosphorus, aluminum and nitrogen. So do the ions, do the diagram, chemical formula, and chemical name. You're welcome to work with somebody else, but I would encourage you to work with somebody else. And this is where having those first 20 elements memorized can be really beneficial to you, because you already know what those symbols mean and their names are. You don't have to look it up every single time. If you don't remember all of them, they will start coming back to you as we go through this unit. That's a good idea to practice. Okay, so your homework is to upload a copy of today's notes, to this post, and that should include the table. So it should have the drawing, Lewis dot diagram drawings, the naming of the compounds, all the kind of stuff. If you can't remember how to do Lewis dot diagrams, and my little lesson today wasn't quite enough to help you get through that, there's lots of stuff on YouTube. You can also email your teacher, and we can help you out with that as well. Okay? Take care, guys. Everyone's staying home safe and having a good day.